Alright, hello class. In this video we're going to continue our discussion about approximating area under curves. And as I mentioned, there isn't a whole lot more to do with this really. I did want to show another example, but I also wanted to show some notation that can help us going forward. And you will see if you, definitely see if you go on to take Calculus 2 or some statistics classes and various other higher level math classes. Okay, and that's what I'm actually going to start with is this notation that's going to help us out. Okay, and then we'll look at another example of approximating area under curves. And all right, let's get on with it. Okay, so in one of our previous examples, you'll recall that our estimate ended up being something like this. We had our estimate was something like 1 squared plus 2 squared plus 3 squared plus 4 squared, on and on and on up to like 7 squared. Okay. Now if we were actually to write this all the way out, you know, it gets kind of tedious, and especially if it ends up being all the way out to like 100 squared, right? There are a lot of terms there. So we actually have notation in mathematics to describe this in a more efficient way. Okay, and that's called sigma notation. All right, in sigma, we use the capital sigma, right, which is a Greek letter, and it kind of corresponds with the letter S. So we're kind of saying that this is basically S for sum. Right? And so here's how the notation would work. Let's say I wanted to write this particular thing here in sigma notation. So how I would do it is I'd write my sigma, and I would use some sort of iterative letter. You could use K, you could use N, you could use W, it doesn't really matter. Okay, but I'm going to have K starting at 1 and going to 7. And specifically, we will be summing k squared. Okay, so this tells you that we're going to be summing k squared for k equals 1 to 7. So if we were to work this out, we'd get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Okay. So how this essentially works is with our capital sigma, we're going to sum stuff. So right here is going to be our starting point and variable. Okay. And then up here we have our ending point. And in here, this is what we will sum. So this is often called a sum and, which is, I always have trouble saying, but it's kind of like an integrand, right? Sum and. And that's essentially how this notation works. It tells you how we are going to sum things up. So for example, if I said, all right, let's take the sum of k starting from 2 and going to 10 of cosine of k. Well, it would literally be summing up a bunch of cosines of k starting at k equals 2. So it'd be cosine of 2 plus cosine of 3 plus cosine of 4 all the way up to cosine of 10, right, wherever our starting place is. So that is just a more efficient way of writing this in sort of a smaller amount of characters, right? So to give another example, let's say we have this sum of k starting at 10 and going to 20 of 1 over k. Okay, well this would be, we'll start at 10, 1/10, plus 1/11 plus 1/12, plus 1/13 all the way up to plus 1/20. Right, so you were always iterating this by a factor of 1. Okay. If we didn't want to do it with a factor of 1, there are lots of little tricks we could do to kind of make that happen, but typically we always are counting that iterative variable by a factor of 1 each time. All right, and as I said, this notation, it will be used quite a bit, especially in Calculus 2, but for right now, knowing the basics and when I throw it out at you, knowing kind of what it means, that should be good enough for right now. Okay, so let's look at some more examples of Riemann approximation, Riemann sums. All right, so let's find the left, right, and midpoint Riemann sums of this function. Let's say it's f of x equals 1 over x on the interval 1 to 5 with 4 subintervals. So to start with, I want to look at my delta x, which again is our b minus a over n. So in this case, it's going to be 5 minus 1 all over 4, which is 4 over 4, which is 1. So the length of our subintervals is 1. Now, if we were to set this up 1 to 5, that should hopefully make sense, because if we go 1, 2, 3, 4, 5, let me make sure these are even. Okay, that does split the interval 1 to 5 into 4 subintervals with equal length. Okay, so our delta x here is 1. Okay, now like before, if we want to do our right-handed estimate, that's where we start on the right-hand side to get our heights for the rectangles. Right, so we'll use f of 5, f of 4, f of 3, f of 2, and our delta x is going to be 1. So it will be delta x times the sum k going from 2 to 5 of f of k. Okay, which will actually end up being delta x in this case is 1. So it'll be 1 times the sum k going from 2 to 5. Well, f of k is 1 over k. Right, so that's what we'll be looking at. We'll be looking at the sum k going from 2 to 5 of 1 over k. So 1/2 plus 1/3 plus 1/4 plus 1/5. All right, so this is about 1.283 repeating. Just the 3 is repeating. That should just be an equal. So that's also 77 over 60 if you wanted to have it as an actual fraction. Okay, so there is the right-handed estimate. All right, just real quick, here's the graph of f from 1 to 5, and here are the right-handed rectangles. Now, you'll notice that in this example, the right-handed rectangles end up being an underestimate, where in the previous example, they were an overestimate. And that really has everything to do with the concavity of the graph. Right? Based on the concavity, will the right-handed or the left-handed be the over or underestimates? That's really what it comes down to, and sometimes it switches, right? Wherever the concavity ends up switching. Okay, so now let's take a look at the left-handed estimates. Okay, for the left-handed estimates, again, here we use the left-hand side to get our height, so we'll be using f of 1, f of 2, f of 3, and f of 4. Okay, so the left-handed estimate will be delta x, and the sum, k going from 1 to 4 of f of k, which, actually I'll just write it that way, f of k, and that will be the 1 times the sum, k going from 1 to 4 of 1 over k. Okay, so it's going to be 1 plus 1/2 plus 1/3 plus a fourth. All right, which comes out to be about 2.083 repeating. All right, just to be consistent, here's the graph and the left-handed estimates using the left-hand side for those heights, and you can see in this case it's the left-handed estimates that are the overestimates when compared to the right-handed estimates. Right, and third up, we use the midpoints. So for the midpoints, again, we'll use f of 1.5, f of 2.5, f of 3.5, and f of 4.5. Okay, so you might wonder how we would write that for our midpoint estimate as a sum, right? But it's going to be k going from 1 to 4. And instead of just f of k, it's actually f of k plus 0.5. Right, so it'll be 1 times k going from 1 to 4 of 1 over k plus 0.5. And if you think about it, right, you put in the 1, you'll get 1 plus 0.5, which is 1.5. You put in the 2, you get 2 plus 0.5, which is 2.5. Put in the 3, 3 plus 0.5, etc., etc. So this does come out to be 1 over 1.5 plus 1 over 2.5 plus 1 over 3.5 plus 1 over 4.5. All right, which comes out to be about 1.5746-ish. It doesn't actually come out to be a super nice fraction. The actual fraction is 496 over 315. So I would just use the decimal here. And there we go. All right, once again back to the graph. Here's the graph itself, and here's the midpoint Riemann sum. And if we put them all three together, you can see how they all compare. Right, and here we have them along with their values. Okay, now I would greatly suspect that it's the midpoint one that is closer to the real value, although we do have a lot of stuff going on here. Okay, but there we go. Now let's take a look at another example. All right, so for our next example, let's find the left, right, and the midpoint Riemann sums of the function f of x equals e to the x over 2 on the interval 1 to 4 with 6 subintervals. So first, we'll calculate our delta x, which is going to be 4 minus 1 over 6, so 3/6, so 1/2. So our intervals have a length of 0.5. All right, so when we set this up, going from 1 to 4, right, here's 2. Whoops. Sorry, more like there. Here's 2 and 3. And then here's 0.5 or 1.5, 2.5, and 3.5. So this is the length of our subintervals. That's our delta x. And that gives us the 6 equal bases, right? 1, 2, 3, 4, 5, 6. Now from here, it just follows exactly as we've been doing before. Right, for a right-handed estimate, we use the right-hand side. Right, so 1.5, 2, 2.5, 3, 3.5, and 4. All right, so our right-handed estimate comes out to be, well, it's delta x times the sum, k going from 1 to 4. Okay, actually, I think I should talk a little bit about how we would scale this. So we're actually taking steps of 0.5. So let's talk about how we would actually write that in sigma notation. Okay, so here's what we basically want. When we plug in k equals 1, we want that to correspond with 1.5. And when we plug in k equals 2, we want that to correspond to 2. All right, so it looks like when here, if I wrote this as 1 plus 0.5, so that's actually 1 plus a half. And this is actually 1 plus 1, or 2 halves. Okay? And when I plug in k equals 3, I'm going to want 2.5. So that would be 1 plus 3 halves. Okay, so I think I found my pattern here, that it's actually k needs to go to 1 plus k halves. Because when we plug in the 1, we'll get 1 plus a half, 1.5. When we plug in the 2, we're going to get 1 plus 2 halves, which is 2, 3, 1 plus 3 halves, which is 2.5. When we plug in the 4, we get 1 plus 4 halves, which will be 1 plus 2, which is 3. When we plug in 5, we'll get 1 plus 5 halves, so that's 2.5, so that will give us 3.5. And then if we plug in k equals 6, we'll get 1 plus 6 halves, 1 plus 3, which is 4. So it looks like that is what we're looking for. K going from 1 to 6 of f of 1 plus k halves. Now, I will note, you don't have to do this, okay? I'm just doing this to show you how you would go about doing it. You can't just write out the sum if you want, all right? Because this is going to be, now remember, our delta x here is 0.5, so it'll be 0.5 times the sum, k going from 1 to 6 of e to the, and here's where we need to be careful because it's x to the 1/2, it'll be 1 plus k halves divided by 2. Okay? Or you could just write out this sum as e to the 1.5 divided by 2 plus e to the 2 divided by 2 plus e to the 2.5 divided by 2 plus e to the 3 divided by 2 plus e to the 3.5 divided by 2 plus e to the 4 divided by 2. Okay, this is really something that will be more important later on. Okay, but for right now, you could just write this out. I was just showing how you might if you were interested. All right, I got that. That's about 12.975. Right, and if we go to our graph here, look at the right-handed estimates. So here's our f, and here's our right-handed rectangles. All right, let's do the left-handed estimate now. I won't bore you with the k stuff. It would work the same way, but this will be delta x, k going from 1 to 6 of f of 1. Oh, sorry, in this case, instead we could do 0 to 5, right? Because remember, we aren't going all the way out to the 6th place. Last time we started at the 1. Here we'll start at 0, end at 5, and get the same thing. But ultimately, it's just going to be 0.5 times, in this case, f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5. All right, if we look at the graph here, and I guess I should have wrote this here, but we get about 10.105, and here it is on the graph with our left-handed estimates. And then finally, we will look at the midpoint estimates. All right, so for the midpoint estimates, we're going to look in between. So between 1 and 5 is 1.25. Between 1.5 and 2 is 1.75. Between 2 and 2.5 is 1.25. Then we'll have 2.75. We'll have 3.25 and 3.75. Okay, so the midpoint estimate will be 0.5 times all these values, f of 1.25 plus f of 1.75, etc. Just realized I had a typo there. That should be 2.25. All right, and here we got about 11.45. Right, so when we look at the graph, here's the midpoint version of it with 11.45. So if we look at all three, okay, we could probably guess that the actual area beneath this curve probably close to 11.5 or so. Right, it's definitely going to be between 10 and 12. All right, so let's look at this final example. This final example is looking at a situation where you're given a table, all right, but it works in much the same way. So we're given values for x and f of x, and we want to find all of these sums on this interval. We're looking at 1 to 10, okay, and I want to start with, let's use 3 subintervals. Okay, so we approach this in exactly the same way we usually do. We start by finding what our delta x is. So of course that's b minus a over n. So it's 10 minus 1 over 3, so that'll be 9/3, which will be 3. So the length of our subintervals is 3. So we're going to be going from 1. Right, then we'll go 3 over 1, 2, 3 to 4. Okay, then we'll go 3 over 4, 5, 6, 7, 7, 8, 9, 10. Okay, so what we've basically done is set up an interval 1, 4, 7, 10. Okay, which is a little strange, I know, but this has given us 3 equal subintervals. Okay, and so from here, we are going to use or set up our left, right, and midpoint estimates. So for the right-handed estimate, we're going to just use 10, 7, and 4. Okay, so it will be delta x times f of 4 plus f of 7 plus f of 10. Okay, so our delta x here is 3, and then the f of 4, 7, and 10 we get from the table. Right-handed, sorry. So f of 4 I get from the table, which is 1. F of 7, which is 5, we get that from the table, right? And then 10 is also 1. Okay, so we get 3 times 7, which is 21. I don't know why I wrote it 3 there, but 21. Okay, so there's our right-handed estimate. For the left-handed estimate, okay, left-handed estimate, we are going to instead use 1, 4, and 7. Right, so it'll be delta x times f of 1 plus f of 4 plus f of 7. So our delta x is 3. And then we'll get these values from the table, right? F of 1 is 3, f of 4 is 1, and f of 7 is 5. Right, so we get 3 times 9, which is going to be 27. All right, I'm not going to do the midpoint here because the midpoint between say 1 and 4 is actually 2.5, and we don't actually have that value in the table. So you can't get values from the table that you don't actually have. Okay, so there we go. That's our right-handed estimate and left-handed estimate from this table, just using 3 subintervals. However, we could also use more subintervals to split this into more pieces. So for part B, what we're going to do is look at this with, let's do 9 subintervals. All right, so we're looking at the interval from 1 to 10, and we're going to do 9 subintervals. So again, our delta x will be 10 minus 1 all over 9. 9 over 9, so the length of our intervals are 1. So we'll be using every one of these pieces on the table, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that's going to give us 9 equal subintervals. Okay, so the right-handed estimate will be delta x times, and we're just going to use the right-handed values to get our estimate. Okay, we're not going to use the leftmost. Okay, so we'll have f of 2 plus f of 3 plus f of 4 all the way up to plus f of 10. Okay, and in this case, our delta x is 1, and then we just get the values from the table, right? 5 plus 2 plus 1 plus 0 plus 7 plus 5 plus 4 plus 2 plus 1. All right, and I got, when I did this, about 27. Hopefully I'm not incorrect there. And then for a left-handed estimate, we're going to go from 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 10. Okay, so it'll be delta x, and I'll go ahead and use the sigma notation here, k going from 1 to 9 of f of k. Okay, so that's going to be 1 times, be 3 plus 5 plus 2 plus 1 plus 0 plus 7 plus 5 plus 4 plus 2. All right, and I got 29 if I did that correctly. And so this is how you tackle problems with a table. If we had a more even setup, we could also do midpoints by picking the things halfway between. We don't have those midpoints, so unfortunately we can't actually do that. But yeah, there we go. There's our how we do our Riemann sums given a table. It works pretty much the same way as with a function value itself. It's just those values are already given to you. You don't actually have to calculate them. You're just using the table. It's almost easier with the table, in my opinion. All right, I think that is definitely good enough to get you rolling on the homework. And in the next lesson, we will take that idea that we've talked about in here, where the more rectangles we have, the closer approximation we get to the actual area. All right, and we'll talk about what that actually gives us moving forward. All right, so I'll see you all in the next one.